This is a Bendix G-15, a full-fledged vacuum tube computer from 1956. It was designed by Harry Huskey, and he worked with some absolute giants in the field. Notably, he worked with Tommy Flowers and Alan Turing, and this is kind of like a spiritual successor to Alan Turing's Pilot Ace. There's about 460 vacuum tubes inside, around 3,500 germanium diodes, and this machine is fully working, making it, I believe, the oldest running digital computer in North America. So how did such a historically significant machine end up here in a tiny little shop out in the middle of nowhere, Texas? Well, this one's on loan from Bob over at System Source Museum. And if you haven't heard of System Source Museum by now, what are you doing? Go check it out. It is amazing. System Source Museum is one of my all-time favorite places on the planet. The collection there is breathtakingly good and constantly changing. As a matter of fact, all of the B-roll footage that I'm showing now is now outdated because it's been too long since I've been back there. So I really need to get back up to System Source just to give Bob a big high five and see all the new stuff. But also I need to get back up to System Source to deliver this machine because it came down so we can get it fully working. And yeah, it fully works. Kind of. The reason that we haven't delivered it yet is because there's still one big hurdle that's messing with us. And that is the typewriter. The typewriter is hot garbage. It's so bad, man. It's just been, we're gonna work on the typewriter today. So what is our typewriter doing? Well, first we should remind ourselves what the typewriter should be capable of doing. And the Bendix G-15, or this model of it, is a numeric-only machine, which means it's primarily dealing with just hexadecimal. There's a lot of keys that we don't care about, like A and B, for example. They don't do anything. So we're not even going to concern ourselves with those. But even of the finite amount that it's capable of printing, we have lots of problems. Some things aren't printing at all. Some things are very weak. So I got in touch with our good friend Bill, who wrote Doom for the G-15, which played beautifully well. And he wrote this little test routine right here, which is a typewriter test routine. This should test everything the typewriter is capable of. And this highlighted a lot of problems. So we have dash, period, space, and 6 failing to decode. What this means is that the hammer never swings and the platen never advances. So there's a problem in the relay matrix somewhere. Then we have 5, 7, U, and Y. These are decoding properly, but they're very weak. The hammer swings, but it never makes it all the way to the platen. This has to do with that rubber friction roller on the bottom. That thing is getting smooth and needs a little more work. And finally, V is encoding and decoding as plus, which is weird. Like the Bendix G-15 shouldn't even be capable of sending or printing plus. We're gonna have to see if we can maybe fix that, or maybe we'll just leave a little note on here that says V equals plus. But as you can see, there's a lot wrong with this thing. So let's get it over on the bench and get to work. Getting it over to the bench is no easy task though. The typewriter itself is heavy, but when you add in the ridiculous 28-inch platen, it's ludicrous. Thankfully, I'm on that vintage computer workout routine and I can get the beast over to the table. To get inside this thing, we'll flip it up onto its back. Then the 4 rubber feet are also the mounting screws. Each one just unscrews from the studs inside, and then the whole bottom rotates down, giving easy access to everything. Let's separate the bottom plate from the mechanical bit completely by unplugging the 2 cable connectors that go between them. Then to get access to the relay matrix, there are just 2 plates, each held on with 2 screws. Loosen those up and both plates pull up and off with ease. Now I've been calling this a typewriter and not a teletype because it absolutely is not a teletype, which seems weird because communication between the typewriter and the G-15 is 5-bit based, and if you're already sending 5 bits, why not lean into that serial Baudot standard that had been around for decades by this point? Well, it turns out that Bendix had some pretty strict requirements that a teletype would not have been able to meet. The first is speed. This thing types ridiculously fast, faster than I've ever seen any 45 baud teletype type. And that's because it's not sending data serially, it's sending it in parallel. The other is that there's a bunch more special communication that was necessary that a teletype would not have been able to do. So I've got a full list of the communication here, and you can see that if we're talking about what the typewriter receives and needs to print out on paper, if the 5th bit is set, the remaining 4 bits are interpreted as a hexadecimal number and it needs to type that out. However, if that 5th bit is not set, then we look at the first 3 bits and interpret those into a space, minus, carriage return, tab, reload, which is a slash character, or a period. Now, where things start to get a little confusing is what the typewriter sends back to the G-15. There's so much more that the typewriter is sending to the G-15 that can't be covered by this 5-bit standard. If we look down here, we have SA, which is the typewriter enable switch on and off, main punch, which is the punch enable switch on and off. We have go, not go, and breakpoint, which is the compute switch on the front here. And then if you press specific keys on the typewriter keypad up here, they mean different things. So if I press the key I, that tells the machine to perform a single cycle. If I do C, this sets the command line to 00. P starts a phototape read. And all of these additional special signals are sent down their own individual wire, which is why this thing has a massive Canon connector that plugs into the back of the machine. So that means that when I type the letter S, there's a row of contacts up here that get made to send a signal into this diode matrix, then breaks that signal out to its own individual wire and sends it off to the machine. Now, when the G-15 is sending data back to the typewriter, that 5 bits arrives and goes through this relay matrix. The reason that we're using a relay matrix instead of a diode matrix is because we're also sending like a colossal amount of voltage and current, because that signal goes through the relay matrix all the way up here to an individual solenoid that then actuates and physically pulls the key on the typewriter, which is why you can see the keys doing all sorts of hilarious stuff whenever this thing is printing out. Now, if we have a decoding problem, that has to be in the relay matrix here. Now, the last time I did this, I did it with sandpaper, and the comment section exploded. And I've heard you, I'm not going to use sandpaper on relays anymore. As a matter of fact, a good friend of mine has hooked me up with some proper tools to do that. So I think that's our first step. A buddy of mine, John, sent me this excellent relay burnishing and adjustment toolkit. We're going to make use of these 2 burnishing tools today to really clean up the contacts of the relay matrix. Everything on this matrix is so dainty and small, which makes sense. Their top priority is speed, so the relays have an incredibly short travel distance. The burnishing tools are actually thicker than the travel distance of the contacts. Next, let's see if we can get the hammer swinging a little harder. I'm going to use some of this rubber Renew by MG Chemicals. This stuff is brutal. It smells incredibly strong, and you definitely have to wear gloves. I'll just soak it into a shop towel, then work that into the friction roller. This should cause the rubber to swell temporarily, letting me scrub all the dirt and grime out of it. Then once it dries, it should shrink back to its normal size and remain tacky. And once everything is back together, let's give this thing another test. That is definitely an improvement. It's looking much, much better than it was. Well, that wasn't the slam dunk that I was hoping it would be. It was pretty close to a slam dunk. I ran that typing test program a ton here. Actually, it continues on to the next page. And a lot of stuff has improved. 5, 7, U, and Y are still very weak, so I think I need another run with that rubber Renew. Dash, period, and space are now decoding properly in the relay matrix and printing out just fine on the paper. However, 6 is still not doing anything. The hammer never swings, the platen never advances. But I'm like 99% certain that the relay matrix is now working perfectly. So I needed to shift my focus right up to here where the solenoids are. This backing plate that we're looking at right here that has a bunch of seemingly randomly placed screws on it is a support plate for the solenoids that are behind it. These are the solenoids that pull on the individual keys. And they're all numbered, and lucky number 13 is solenoid 6. And if I take my multimeter and I measure across 13 there, it's open. If I measure across any of the other solenoids, I get about 330 ohms-ish. It's a little different per solenoid, but those are all good. So solenoid number 13 here, which is our number 6, has gone open. Now, interestingly, we can also see the modification that causes V to decode as plus. That's this extra wire right here at the top that has been soldered over here to solenoid number 4. But that's a bit of a mystery. And that mystery is not in how it was modified, that's pretty obvious here, but the fact that it even could be modified to do this. Because if we look through the documentation, it never mentions plus. It should be impossible for this typewriter to type plus. So why on earth did Bendix put an extra solenoid in on the plus key and leave it unwired? And why did somebody take advantage of that, rewiring V into plus? I don't know. I don't have the answer for this. This is super weird, but it does provide a solution to our problem with the 6 key being burned out, because that means that there's an extra solenoid that's not being used, because the V solenoid over here is currently unwired. So we can fix our V decoding problem. And then I can take the spare plus solenoid over here and swap it with the burned out 6 solenoid, and we can have our typewriter fully functional again. I'm not entirely sure how to get this whole thing apart, but all the solenoids are bolted to this plate, which means that in order to get a single solenoid out, the plate's gotta come off. And with it out of the way, here we are, all the solenoids plainly marked. If we check the manual, solenoid 13 is our burned out number 6 solenoid, solenoid 20 is our disconnected letter V solenoid, and solenoid 4 is our plus symbol solenoid, although that one isn't shown in the manual. In order to get a single solenoid out though, it's going to require a bit more dismantling. First step, let's get the top off. It's just 2 long bolts and then it pulls right out of the way. Next up is I have no idea what this control wheel does, but it's in the way, so off it comes. On the other side, we'll do the same procedure to remove the power switch wheel. Then there are 4 screws, 2 per side, holding the solenoid block in place. With all 4 removed, the whole block can be slowly walked backwards, ultimately pulling free. But this leaves behind an absolute nightmare. All of the plungers for the solenoids are still connected via springs to the key bars. They'll have to be completely realigned to slot into the solenoid bodies during reassembly. But we can see how this thing actually types. When power is sent through the solenoid body, it creates a magnetic field that pulls on the plunger. The plunger is connected to a type bar via a spring. It's the most hilariously brute force way of getting a typewriter to type, and I absolutely love it. All right, let's get to work repairing this thing. The first step is to desolder the wires for the burned up solenoid. Each solenoid is locked in place with a grub screw, and a quick turn lets the solenoid body move freely, which it then can be slid right out easy peasy. We'll repeat the process for solenoid number 4, which is our plus symbol solenoid, and this is going to be our replacement for solenoid number 14, which is the 6 key solenoid. We'll no longer be able to type plus, but we shouldn't have been able to in the first place. Anyways, I solder the solenoid wires back onto the terminal posts. Then I'll remove the extension wire that rewired V to plus, and I'll resolder the original wire back to where it's supposed to be. Finally, I can start the long and arduous process of getting each and every plunger lined up with the appropriate solenoid body. I did this with hemostats and a whole lot of patience. I thought about dangling the typewriter over the edge of the table, but if the thing fell while I was under it, I'm pretty sure it would have killed me. So I opted for the less deadly option of using hemostats. Ultimately, I got there and got the solenoid block back into position. Okay, we've got problems on the encode side here. Nothing seemed to be really matching the manual very well, so I went through and mapped out what each key connects up to for which switch. And I'm discovering all sorts of weird stuff. Switch number 31 all the way on in here looks like the wire has broken off. That is the space key, but not the space bar. It's the extra unmarked small key on the inside. This is a legitimate space. Whenever the machine is typing spaces, it uses that key. The next big problem is that wire number 14 here has been soldered to this second to last switch here, which is the plus key. So this should be V, which should be soldered all the way over here. And I can see where it's been removed or something used to be soldered here, but they also removed my spring that connects it to the foot down here. And in order for that to make sense, we got to kind of wrap our head around how things work here. We've got our primary friction roller down here, and this thing is just going to always be spinning. And then whenever you press a key, a little foot gets pushed down into the friction roller, which then catches it and slings it around to actually throw the hammer. But when that foot gets pulled down, there's a spring connecting that foot all the way up to this screw. So that way when the foot gets pulled down, it pulls on the screw and makes a connection. So if I push the letter F here, you can see that that connection gets made right here. The problem is that the V key goes here where the spring and screw have been removed. And that is hyper annoying because even if I resolder pin 14 over to here, this never actuates because there's nothing to pull on it. Again, I have no clue what the best way to tackle this is going to be, so I'm just going to take stuff apart until I regret my decisions. And I did manage to get the contact block loose, but only just. It's still refusing to move more than about a centimeter in any direction. Next, I'll try loosening up the clamp bar for the individual contacts. I couldn't get it all the way out because the solenoid block was in the way, but I did get it loose enough, although I don't really think this was a necessary step. All I really needed to do was grab the spring with some hemostats and remove the screw that threads into the spring. The spring I'm stealing is from the semicolon, which isn't used by the numeric control typewriter at all, so we're not sacrificing any functionality by doing this. I'll slot it into place and get it hooked around the foot that hits the friction roller. After a lot of work, when I press the V key, it does appear to be pulling on the contact properly. Next, I need to rewire the contact into the appropriate place in the loom. I'll snake a new wire through the original wire lacing, then solder it into place on the V contact. And now, whenever someone in the far future opens this up, they'll be genuinely perplexed as to why there's a random green wire in the middle of everything. All right, moment of truth. I had so much stuff apart that I'm not actually all that confident that it's gonna work, but it is all back together for the time being. So we're gonna load up Bill's typewriter test program here. I do believe that it has number track on it already, so we should be able to just hit reset here. The sequencer is going to kick off, which is going to load in the first two blocks off the tape here. Block 1 should be number track. And then block 2, which is loading in now, is going to be the first block of Bill's program there. Uh-oh. Looks like we had a tape problem. It folded over on itself. Well, that's not good. All right, because the tape folded over on itself, this gets a little more difficult. We're gonna do an enable on, and I'm gonna hit the P key, which is gonna start a phototape read. That's good. That's the first block again. That's putting that into line 19. All right, we're gonna do an enable P again, turn enable off, and that should have loaded in his entire program. So let's flip the switch to go here. I think everything worked. Let's take a look. I should be able to hit S here, and it should type again. Yes. All right, now I should also be able to punch in 7 digits here. So we're going to do the 2 that we were having trouble with. 6V, 6V, 6V6. And then I can do a tab / S. It'll do a carriage return, and something didn't go right on that, but I don't know if that's a typewriter problem or a program problem. So what did this teach us? Well, we learned that programming the G-15 is still absolutely a challenge. There's a couple of bugs in here. Notably, we have a carriage return bug where after I type S, sometimes it does a carriage return, sometimes it doesn't. And I think we figured this one out. We're not waiting enough drum revolutions before starting the type out after receiving a type in. But that's a software problem, not a hardware problem. This test has illuminated a pretty nasty hardware problem though, because on the next line I type 6V, 6V, 6V6, and if I type 7 digits, then a tab, then an S, it should repeat those 7 digits in the first field, but instead we get 15U6666, which means that my 6s are getting received by the G-15, but my Vs are not. We get further confirmation of this lower down when I type VVWWXXY, and I get 5UWWXXY. So the V is just not getting sent, which is frustrating because everything else seems to be working. So I had to do quite a lot of surgery to get that V going. I bet you I've just got something adjusted incorrectly, but if we can get that going, I think the typewriter is going to be at 100% working again. So let's pull it apart and take one more stab at that V key. Okay, let's check that the contact is still good first. And yeah, the multimeter is showing good connection when I push it by hand. But if I press the V key, it doesn't pull the contact anymore. And this is why. The spring popped off of the foot. After getting it hooked back up, it seems I left a little too much slack in how far down I screwed in the bolt. I'll cinch it down fully, which is a bit of a nightmare since springs tend to flop about. And now I've got the opposite problem. The contact is always on. This thing is putting up one heck of a fight. The hemostats came back out, and I just spend the next 30 minutes adjusting and checking over and over again. Finally, I get it there, and I'll take this opportunity while it's all apart to do another run with the rubber renew. The friction roller is so much better than it was, but we're still weak with the U and Y, so I'll just focus on that location of the roller this time. Hopefully it was just a simple adjustment. Let's flip the compute switch to go. All right, that's what we were expecting it to do. Now let's see if we can send Vs. I'll type V 7 times. 1, 2, 3, 4, 5, 6, 7. We'll do a tab, S. Yes! And there it is. I sent 7 Vs in, they were received, and they printed out perfectly right over here. So our V key is fully functional now. And if we look just above that, we can see that we've got 0, 1, 2, 3, 4, 5, 6. Then we have a tab, then 7, 8, 9, UVWX. Then we have another tab. My tabs are misaligned terribly. And then we have YZ 0, 1, 2, 3, 4. That's everything that this thing is capable of printing. This typewriter is fully repaired. And there we have it. If I reach over here and I type S, the typewriter starts hammering away. Music to my ears. Oh man, this typewriter has been battling us since day one. And for it to sit here and punch out every single character perfectly, even our U's and Y's are now extremely legible. It all works. The typewriter is 100% repaired. The Bendix G-15 is 100% repaired. These two together are done. The Bendix G-15 project is done. We're ready to send this thing back to Maryland to go on display at System Source Museum so they can fire it up and you can get hands-on with this machine in person. But before we load it up and send it out to Maryland, there is one more thing that I want to do with it. And a lot of people have asked me, what can it do? I mean, everything we've done up to this point has been heavily focused on the hardware. And we did dive into writing assembly for it, but that was really esoteric and kind of difficult to understand. So what was this machine actually used for? How did people use it in anger back in the 1950s? And what can it actually do? Well, that's what we're going to get into in the next episode. So I want to thank you all so much for watching, and I hope to see you then.